Hello students, today we will discuss about effects of nucleophiles leaving groups, only these 2 points in nucleophilic substitution reactions. Later we will discuss about the phase transfer catalysis and Crown methods. First we will see the effects of nucleophiles on the reaction mechanism of nucleophilic substitution reaction. First we will see that nucleophilicity and basicity may be correlated since both involves the availability of electron pairs and the ease with which they are donated. However, they are not exactly the same. There are differences between nucleophilicity and basicity. Like basicity involves electron donation to hydrogen, whereas nucleophilicity involves donation of electron pair to another atom. And basicity involves an equilibrium reaction with a proton, so it is a thermodynamic character. However, nucleophilicity is a kinetic aspect, and next is like basicity is less affected by steric influence, whereas nucleophilicity is largely affected by steric effect. As you know that SN2 reaction is hindered if there is steric hindrance around the electrophilic center. Okay, next we will discuss about hardness and softness. So hard base, what is a hard base? I think you guys already learned in your acid base classes that hard base is those substrates which have high electronegativity, low polarizability, and they are hard to oxidize, such as hydroxide and alkoxide and amines. Whereas soft base are those in which donor atom is of low electronegativity, high polarizability, and they are easy to oxidize, such as sulfide, iodide, thiocyanide. You should know, you should understand that softness of a base or a nucleophile increases the nucleophilic character of the nucleophile. So if we compare sulfide and alkoxide or hydroxide, we will see that sulfides have more nucleophilicity than alkoxides, because sulfur atom is more polarizable. Therefore, they can donate electron pair more easily to the electrophilic center. That's why sulfides are more nucleophilic than alkoxides. Similarly, if we consider along the row in a periodic table, that iodide, bromide, and chloride, if we consider the nucleophilicity between these three ions, then we will see that iodide is more nucleophilic than bromide, and bromide is more nucleophilic than chloride. Why this is? Because iodide is more polarizable, and this is a soft base, and it can donate electron more easily due to its larger size. It can act as a good nucleophilic center. Similarly, bromide is more nucleophilic than chloride. So we understand that softness increases the nucleophilicity, and we will now look at the fact that if the attacking atom is same, then the basicity and nucleophilicity runs parallel, means stronger the base, more the powerful the nucleophile is. Here you see O minus is the nucleophilic center in different nucleophiles like ethoxide, phenoxide, acetate, and nitrate. Now if we compare the basicity of these four nucleophiles, then we will see that the basicity order is like that. Ethoxide is more basic than phenoxide, and phenoxide is more basic than acetate, and acetate is more basic than nitrate. And the similar trend is observed when we consider the nucleophilicity. So you guys understand that when the nucleophilic center is the same, that O minus, then basicity and nucleophilicity runs parallel. Clear? Okay, next we will discuss about the effect of nucleophilicity on mechanism. You know, in SN1 reaction, the rate determining step is the formation of the carbocation. There is no involvement of the nucleophile. Therefore, the nucleophilicity is not important. The nucleophilicity is not an important aspect in SN1 reaction. However, in SN2 reaction mechanism, you know that the nucleophilic attack on the center, on the electrophilic center, is involved in the rate determining step. Therefore, nucleophilicity is more important in SN2 mechanism. So, with a good nucleophile, the rate of SN2 increases, and with a good nucleophile, there may be changeover in mechanism from SN1 to SN2. So, you guys understand that the nucleophilicity, the nucleophile is very strong, very good nucleophile, then there will be an increased rate of SN2 reaction, and there may be a changeover from SN1 to SN2. A nucleophile, another point we will discuss about, that a nucleophile with a negative charge is more powerful than its conjugate acid, assuming that the latter is also a nucleophile. If we consider hydroxide and water, water is the conjugate acid of the hydroxide. So if we consider the nucleophilicity of these two substrates, then we will observe that hydroxide is more nucleophilic than water. Water sometimes also act as a nucleophile. You will see in your different classes of organic chemistry classes. So you see that hydroxide, which contains a negative charge, is more nucleophile than its conjugate acid. Similar is the case of amide, which is more nucleophile than amine. Okay. And next we will discuss about when the attacking atom is in the same row of the periodic table, then nucleophilicity and basicity runs in same order. Okay, so here you see in the same row C minus, N minus, O minus and F minus. These nucleophilic centers belong to the same row. So here the basicity of carbon minus is more than nitrogen minus, and this is more basic than O minus. This is more basic than F minus. Therefore, nucleophilicity of carbanion is more than amide, and amide is more nucleophile than alkoxide, and alkoxide is more nucleophile than fluoride. Okay, I hope this is clear to you. Next, we will discuss about a more important aspect, very important thing about that alpha effect. Alpha effect refers to the increased nucleophilicity of an atom due to the presence of an adjacent atom with lone pair electrons. So, if we have two groups or two atoms which contains lone pairs, like here, like hydroxide, like here the peroxide ion compared to the hydroxide, if we compare the nucleophilicity, then we will see that peroxide has more nucleophilicity than hydroxide. Why this happens? And similarly, here you will see that hydrazine or hydroxyl amine is more nucleophilic than ammonia. Here you see both hydrazine and hydroxyl amine, both nitrogen and nitrogen oxygen contains lone pairs, and they are situating at adjacent. They are there in the adjacent atoms. So you will see that the nucleophilicity is increased of an atom due to the presence of an adjacent atom with lone pair electrons. However, the first atom does not necessarily exhibit increased basicity compared with a similar atom without an adjacent electron donating atom. Means this effect is not observed if we consider the basicity. This is only observed if we consider the nucleophilicity, means if there is an adjacent atom relative to the nucleophilic center, then nucleophilicity is increased, but basicity is not always increased. Okay, what is the reason behind them? The reason behind this is that electron pair repulsion between the two lone pairs makes them more nucleophile. Here you see in the hydrogen or hydroxyl amine, or in the peroxide oxygen, this oxygen and this oxygen both contains lone pairs, so there are lone pair repulsions. So this lone pair repulsions make the lone pair of one center more nucleophilic. And after the nucleophilic attack, the developing charge deficiency in the transition state is stabilized by the adjacent lone pair. Okay, so when a hydroxylamine or hydrazine, one nitrogen center attacks, there is a charge deficiency develops here, which is stabilized by the lone pair of the adjacent nitrogen center. Therefore, the nucleophilicity increases. This phenomena is called alpha effect. Okay. Next, we will discuss about one more important thing, and there are several problems you will encounter in the question papers of university, year-wise question papers, like ambient nucleophile. Ambient nucleophile, which nucleophiles are called ambient nucleophiles? If a nucleophile contains more than one nucleophilic center, suppose cyanide ion, there are two nucleophilic center, carbon center and nitrogen center. We will see if an alkyl halide treated with ethanolic KCN, then alkyl cyanide is formed. However, if an alkyl halide is treated with silver cyanide in ether, then isocyanide is formed. Why this is formed? You see, cyanide has two different nucleophilic centers. Among them, the carbon center is a soft nucleophilic center because it is more polarizable. Okay, because it is less electronegative, not more polarizable, because it is less electronegative. Therefore, it is a soft nucleophilic center. However, nitrogen being a more electronegative center, it is a hard nucleophile. Now, if we consider the first case where alkyl halide is treated with ethanolic KCN, then it is a SN2 mechanism. In the SN2 mechanism, there is partial charge separation on the on the carbon center, which is like delta plus, partial charge separation, and on the halide there is delta minus. So this is the charge density on the carbon center is less, therefore it is a soft electrophilic center. Whereas in the cyanide ion, we already discussed that the carbon center is a soft nucleophilic center because it is less negative, so there will be soft interactions. Okay, in the soft interaction, the carbon interaction will be favored and the carbon center will attack on the alkyl halide, and the alkyl cyanide will be formed. In the second case, if we use silver cyanide, then silver ion, what it will do, it will coordinate with the halide, and there will be the partial charge development on the halogen center, and ultimately there will be the formation of carbocation. Here you see the carbocation, there is a distinct charge, positive charge center is there. Therefore, it is a hard electrophilic center because it has high charge density. So, we already have discussed that in cyanide, nitrogen has the hard nucleophilic property. So, there will be hard interaction which will be preferable. For that, nitrogen will attack to the carbocation and the alkyl isocyanide will be formed. Clear? So, if there is ambient nucleophile which contains two nucleophilic centers, then in different situations two different products will be obtained depending on the reaction conditions and the reagents. If we consider another example, that alkyl bromide, if we treat with NaNO2 in DMF, then the major product will be RNO2, okay, and the minor will be RONO. If we treat with silver nitrate, sodium nitrite, and if we treat with silver nitrite, in the first case we treated with sodium nitrite, not nitrate. In the second case, if we treat with silver nitrite, then the major product will be the RONO, which is the reverse result compared to the first case, where we see RNO2 is major, but in the second case we will see that RNO2 will be minor, RONO will be the major product. Why it is that? In the NO2 minus ion, the nitrogen is a soft nucleophilic center because it has the less electronegativity compared to the oxygen, and the oxygen is a hard nucleophilic center. Clear? Now if we use sodium nitrite in NO2, then there will be SN2 pathway, and we already observed that in SN2 pathway the soft nucleophilic center will attack because the developing the charge separation makes the carbon center a soft electrophilic center, what we observed here. However, if we use silver nitrite, then there will be a distinct carbocation generated, as in the first case we discussed during the cyanide ion, and because it is a hard electrophilic center, then O minus, the hard nucleophilic center, will attack, and the major product will be RONO. Okay, so these are the examples of ambient nucleophile, which gives different products on different reaction conditions. Okay, next we will talk about effect of leaving groups. So you guys know that the carbon leaving group bond breaking happens both in the SN1 and SN2 reactions at the rate determining step. So the leaving group is important. The effect of leaving group is very important for both SN1 and SN2 reactions, because the carbon leaving group bond is broken in rate determining step, and the relative leaving ability is influenced by which factors describes that a leaving group is a good leaving group or a bad leaving group. Those factors are that the strength of RY bond, if Y is a leaving group, the strength of Y bond, the polarizability of the bond, the stability of Y minus, means after Y minus is separated from the alkyl group or the carbon center, how the Y minus is stable, and the degree of stabilization to sulfation of the forming Y minus. The degree of stabilization of the Y minus through sulfation means after Y minus is separated from the alkyl group, how it is stabilized by the sulfation effect, which I have discussed about the sulfation effect of the leaving group in the when we discuss about the SN1 mechanism. Okay, so these four factors are very important. These four factors are very important to dictate the ability of a leaving group. Okay, now we will see nucleophilic catalysis. Iodide is a good leaving group. Okay, iodide is the best leaving group among the all halides. The reactivity decreases along the along these substrates. Like iodide is alkyl iodide is more nucleophilic than alkyl bromide, and it is more nucleophilic than alkyl chloride and alkyl fluoride. why iodide is a very good living group? Because it has large size, means bulky size. The carbon iodide bond is weak, and the negative charge is dispersed and stabilized because iodide has a larger size. That's why the charge density is very less, and it has high polarizability. So all these characters make iodide is a very good living group, and we already have seen that iodide is also a very good nucleophile. Clear? Now if we consider that alkyl chloride is treated with hydroxide and we expect alcohol by nucleophilic substitution reaction, this is a very slow reaction. However, if we add a little bit of iodide in the reaction mixture, then the reaction speeds up. Why this happens? Because iodide, being a good nucleophile, it reacts with alkyl chloride in a SN2 manner to form alkyl iodide. Now in the alkyl iodide, iodide acts as a very good living group, and the hydroxide present in the reaction conditions attack very rapidly on the alkyl iodide to form the alcohol. So and iodide is generated itself again. So iodide is acting as a catalysis, and it is acting as a nucleophilic catalysis. Clear? So it is a two-step process. And if we look at the energy profile, we will see in the first reaction condition there is one transition state, and however in the second case you will see there is an intermediate alkyl iodide formed, and there are two transition states, and the overall activation energy is very much decreased in the second case. Clear? Compared to the first case. That's why the reaction is speeded up after adding some iodide ion in the reaction mixture. This phenomena is called nucleophilic catalysis. This is very important for your examination. And now we will see the anions of oxyacids are good living group. You see triflate, mesylate, tosylate, methyl sulfate. All these anions are very good living group because the negative charge is resonance stabilized over this sulfonium group. Okay, because you see there are several resonating structures you can draw where the negative charge is dispersed over these two oxygens, and because these are very stabilized, so they act as very good living group. As I mentioned earlier, the stability of the Y minus dictates the living ability of a living group. And if you want to methylate, suppose an amine or an oxide or something, some nucleophilic center, if you want to methylate, you can imagine that you use methyl iodide as a methylating agent. However, using methyl iodide as a methylating agent is very difficult, and because it is very toxic and costly, and methyl iodide is explosive. So therefore, if you use instead of methyl iodide like dimethyl sulfate or methyl toluene sulfonate, okay, then you will see the nucleophile will attack here on the one methyl group, and the living group of mesylate will leave, because it is a good living group, the nucleophilic substitution reaction and the methylation reaction will be favorable. Similar is the case with methyl toluene sulfonate. Clear? That's why when you consider about methylating any nucleophilic center, consider about dimethyl sulfate or this compounds as a methylating agent instead of methyl iodide. Okay, next we will see activating hydroxyl group for nucleophilic substitution. As I already discussed with you about that, hydroxide is a very bad living group. Clear? Because the stability of OH minus is less, and the carbon oxygen bond in alcohol is very strong. So therefore the nucleophile cannot easily displace OH minus and forming our nucleophile or nucleophilic substituted product. So what we have to do, we have to activate the alcohol. How you can activate? If we treat the alcohol with tosyl chloride or paratoluene sulfonyl chloride, what will happen? We can prepare that tosylate of the alcohol, and now this tosylate group, the whole paratoluene sulfonate group becomes a very good leaving group, because the generated OH minus is highly stabilized through resonance. Now in the tosylate compound, the nucleophile can attack easily to displace the tosylate and forming the nucleophilic substituted product. Similarly, on alcohol, you cannot treat with sodium bromide for a nucleophilic substitution. Okay, but if we use HBr is a very strong acid. What it will do? It will protonate the OH group to OH2 plus. Now OH2 plus, after leaving, it will form a stable water molecule. Therefore OH2 plus is a very good leaving group, and then in this condition bromide can attack to form alkyl bromide. These things I have already discussed with you, if you can remember. Okay, so hydroxide groups need to be activated for SN2 path, SN2 mechanism or for SN1 mechanism. So for these activations we can do by tosylating, or we can do by protonating the OH2 group. Okay, now we will see that ether linkage can be cleaved with strong acids like HI. What it will do, it will protonate the O oxygen and it will form the positively charged, which becomes a good leaving group, because after leaving it generates a stable phenol group. Okay, and in these conditions I minus can attack easily. Okay, so for cleaving ether linkage you need to use strong acid like HI. And now we will discuss about other nucleophilic substitution. Other means here the leaving groups are not always halides. They are like oxygen and diazonium or nitrogen, etc. So epoxide opening in a nucleophilic substitution with internal is an internal leaving group. With internal leaving group, epoxide here the leaving group is the internal, means it is not separating from the molecule. So epoxide opening is a nucleophilic substitution reaction with internal leaving group. That's why it is comes under the category of other nucleophilic substitution. Okay, and RNH2 group, we can activate the amine by treating with NaNO2 and H plus to make it diazonium, and this diazonium group is a very good leaving group, because after leaving it forms nitrogen, which is gas, and it leaves from the reaction mixture and drags the reaction towards the forward direction, and that's why making amines to diazonium is a good strategy for activating the amine for nucleophilic substitution reactions. Similarly, benzene diazonium ions we can generate by treating aniline with NaNO2 and H plus, which can undergo nucleophilic substitutions to form phenol. Okay, so you see these are a little bit different types of nucleophilic substitution reactions. So with this I conclude the part of nucleophilic substitution reactions, the mechanisms and other aspects. Now, next we will discuss about the role of phase transfer catalysis and crown ethers on the effect on nucleophilic substitution reactions. Okay, thank you for your kind attention.